So I'm going to tell you about a part of the work I did during my PhD thesis at Carnegie Mellon, and so this is joint work with my advisor Eric and Lesong, Amr, and Anker. So during the workshop, we heard a lot about models of networks. So we had random distributions over networks, and if one is given a network, then we can do all nice kinds of things, like we can visualize a complex system, we can detect communities, we can predict the size of a cascade, etc. But in a number of problems, we actually do not get to see a network. We don't know which objects interact with each other, and the focus of this talk is going to be how can we infer connections between objects. In particular, I'm going to be interested in a scenario where we can cheaply measure certain things. For example, in the context of biology, we can measure gene expression profiles, and then we would like to infer which genes interact to drive a development of fruit fly, for example. So the setup will be that we can obtain some measurements over a system that changes over time. And then based on these measurements that can be cheaply collected, we would like to infer something about the underlying complex system. So that's going to be the goal of the talk. And so why do we care about this problem? So in particular, often performing experiments and trying to understand when two genes interact and when do they interact is expensive. So hopefully by having a mathematical model of that can provide some insight into this complex system, we can do this uncovering more cheaply. Okay, so to summarize, we would like to infer some network that tells us about interactions between genes that drive a cell division process, so development of a fruit fly. And we would like to infer these networks from data that can be cheaply collected over time. Okay? So in particular, we have connections, interactions between objects that are changing over time, and we have data that is collected over time. And there are a number of challenges. We will be focusing on problems where the number of observations is smaller than the number of parameters in the model that we would like to make inference about. And so we will utilize, we will assume some structure that underlies the complex system at hand. Okay? And there are other challenges that we thought about, but we won't be talking about those here. So the talk is going to proceed as follows. I'm going to provide you an overview of how Markov networks are used to learn conditional independence, to represent conditional independence assumptions between objects, and how we can infer these conditional independences from ID data. Then we will combine these techniques with some ideas that are commonly used in non-parametric regressions, like kernel smoothing and penalization using total variation norms. I will provide you an application to a data set, then maybe we can talk about some theoretical results, maybe not, we'll see. Okay, so to start off, a Markov network consists of two things. We have a random vector x and the graph that's associated with this vector. The graph, each node in the graph corresponds to a component of a random vector, and edges in the graph represent conditional independence assumptions. And so hopefully this, okay, so this is a useful representation of associations between components of this vector. In particular, a missing edge in a graph indicates that two components of the random vector are conditionally independent. And our goal is going to be to learn this graph structure that underlies a probability distribution P, according to which X is distributed. Two common examples are Gaussian Markov networks and Ising model. These are very nice models because the probability distribution is parameterized by the first two moments. And in particular, the inverse of covariance matrix encodes the structure that we are trying to learn. In particular, if there is a 0 in the precision matrix, this means that the two components are conditionally independent given all the other components. And similarly for the discrete networks, again, the model is parameterized by the first two moments, and if theta AB is equal to 0, that means that nodes A and B are not are conditionally independent. So the task that we have in front of ourselves is, can we learn the structure of a graph given ID data? And so this has been studied a lot in the past 7 years, say, in the high-dimensional context at least. And in the classical setup, there is a nice overview paper by Dutton and Mellon, where they say that if data are Gaussian, we can perform maximum likelihood estimation and test whether an element of the precision matrix is 0 or not 0. In the context of discrete networks, in general, it is hard to learn the structure. But we are interested in the context when the number of parameters is much larger than the sample size. And so recently, one proposal is to, not recent, but in 2006, Manheiser and Willman had a proposal to estimate a structure of Gaussian Markov network by using the following observation, that conditional distribution of one node given all the others. The parameters of this conditional distribution can be estimated by solving the following penalized pseudo-likelihood objective. And then the parameters that are non-zero here will indicate what is the neighborhood of a node. Okay? So roughly, this works as follows. We would like to infer graph between these nodes, so conditional dependencies between these nodes. We form a following objective problem for node 1. We solve the problem. The non-zero coefficients tell us who are the neighbors of node 1. By repeating this for each node, we are going to learn the structure of the whole graph. Okay? And this is nice because it works both for discrete graphical models, for Gaussian graphical models, if a node conditional distribution is a member of exponential family, etc. So it's a very nice idea that carries over to a number of distributions. And furthermore, it probably recovers the graph structure under some conditions, and we have fast estimation procedures for solving this optimization problem at each given node. So what we are going to do is we are going to extend this procedure to more general setting. Okay, so I'm going to, are there any questions? Okay, so the setup that we are interested in is when we have data that is collected over time, and we would like to infer these parameters that hopefully give us insights about this process over time. And in this setting, we have a vector for nodal observations at each time point t, which is distributed according to distribution indexed by a parameter theta of t. This is we are going to allow this parameter to change over time. And g of t is just telling us what the conditional independence assumptions at time point t are. So in particular, it tells us what are the non-zero parameters of what are the non-zero components of this parameter vector at time point t. Okay? So we're going to try to estimate theta, but then once we estimate theta, we'll be able to read off conditional independence structure, hopefully. And we are going to use a general estimation framework. Given a data, we would like to penalize a negative log likelihood. I mean, we are maximizing the penalized log likelihood, and this term is going to measure the fit of the model to the data locally. And the penalty is going to enforce different assumptions on how does the network change over time. And I'm going to tell you about two scenarios. One is when we have smoothly evolving networks, in particular the underlying parameter vector theta as a function of time is smooth in some sense. And another case when we have an abrupt change or some discontinuity in our parameter vector theta. So in the context of smooth networks, we are going to use a local conditional likelihood, a local pseudo likelihood to estimate the graph at estimate the network at a certain point tau. And in the case of abrupt changes, we're going to estimate these networks simultaneously, but by enforcing that the difference between parameters associated to each edge to be small for adjacent time points. Okay? And so just to give you an illustration how this works, recall we have a log of conditional likelihood. We have a weight that decreases as we move away from a time point tau at which we would like to infer the network. And then we are solving a following optimization problem for each a at each time point tau at which we would like to infer the network. So this term ensures that the estimator is going to be smooth, while the penalty is going to ensure that the network estimated at each time point is going to be sparse. So each neighborhood is going to be sparse. And so then we are going to do this at multiple time points tau to get some insights about how does a network evolve over time. And so each optimization problem can be solved reasonably quickly using advances in L1 penalized the solvers that are able to solve this problem. Next, we are going to briefly discuss how to estimate networks with jumps. So here, the model is slightly different. So suppose that these are our parameters. So theta 1, 2 is a parameter associated to edge between node 1 and node 2 at time point t. And this is the plot of it as a function over time. Then we see that there are 4 blocks where the network is constant. So we have here 0.2, 0.5, 0.7, etc., where there's changes in behavior. There's a change in an underlying structure. And so the goal here is to identify where these change points occur, and then to identify a network at each corresponding block. To do this, we are going to again solve a penalized pseudo-likelihood objective. The first term here ensures or biases the estimation towards sparse networks at each time point t, while the second term ensures that the difference between parameters at adjacent time points is small. So this is going to enforce that the whole vector at time point t and time point t plus 1 is either 0 or not 0. And so this is motivated by a fuse penalty, for example, in the context of LSO. But with the difference that here we use L2 norm to shrink the whole vector of differences towards 0. Okay? And again, we can solve this optimization problem efficiently. And maybe just to compare with the previous setup, here we are obtaining a network simultaneously for all n data points, whereas previously we had to solve an optimization problem to obtain a network only locally for time point tau. Okay. And so let me show you briefly an application. How would one use this to explore a real system? So I'm going to focus on estimation of smoothly changing networks. And an application is going to be to trying to understand which genes interact to drive development of a fruit fly. So the data is quite old, from Arvidsman et al. In 2002. It consists of 66 microarray measurements that were collected through a full life cycle of genetically identical fruit flies. So we have independent observation at each time point from a genetically identical fruit fly. And these observations are bucketed into 4 stages. We have a number of observations during the embryo stage, and then as the organism becomes older, we have fewer measurements. The measurements are taken less frequently. So here you have maybe every few hours, and here a few days would pass between we obtain microarray measurements. And we are focusing our analysis to a subset of about 600 genes that are known to be related to development of organism. Okay, so what we are plotting here is just how the estimated conditional independence is at each time point. So not much can be seen here. But let me try to illustrate how this could be used if we post-process the estimated graph. So what we are plotting here is on the outer circle, we have plotted a number of clusters. And so each cluster represents a collection of nodes. And then we connect two clusters if there's an edge going from one cluster to the other cluster, and we ignore edges within nodes in one cluster. And so this is only to illustrate that at certain points there's a transition in the behavior of which genes interact. For example, when the wings start to develop in the adult stage of an organism, there's a huge change between two consecutive time points, because the genes that are involved in development of wings are conditionally dependent according to our algorithm. When in the earlier stage, these same clusters interact with the other clusters of genes, which could illustrate that they perform potentially a different function at an early stage. But this is just an illustrative example of how this could be used. Yes? Yes?
The nodes are the genes?
The nodes are clusters of genes.
Okay, how about the edges?
So edge between two clusters of genes exists if our algorithm has inferred that gene in one cluster and gene in another cluster are conditionally dependent.
Then what do they mean by conditionally dependent here?
So that this, under our model, so we assume that distribution of microarray measurements follows Gaussian distribution. If you don't want to make that assumption, then what I'm saying is that partial correlations between, estimated partial correlation between two components of a random vector is non-zero. Okay. Rob?
In your lambdas or tuning parameters, how were those chosen? Were they chosen to kind of give interpretable pictures here, or stable pictures, or was there some cross-validation? How did you choose those regularization parameters?
So we were maximizing BIC criterion. For the parameter h, we kind of picked it in an ad hoc way. And I don't, besides theoretical guidance.
This is using the kernel one.
Yes, so there are two tuning parameters.
Oh.
Unlike estimation from ID data, where you only choose parameter lambda, here you have the bandwidth of your kernel and parameter lambda that enforces sparsity.
These are with the kernel approach, the piecewise constant.
Kernel approach, piecewise constant.
One was for smoothly varying, one was for jumps. Which one?
So here we are using smoothly changing.
Yeah. And it's kind of impressive that at 8 and 12, you see very similar structure. Is that, how big of a H was there here? I mean, are you using essentially the same data, or is it how narrow is the kernel relative to these times?
I don't remember off the top of my head. I don't know. But sort of the way we chose kernel width was a median distance between all pairwise distances. So roughly you had some constant fraction of data points, and you had this sliding window. So likely that there were only a few points that were used here were used here as well. Okay, so this is just to illustrate how one could use the algorithm to get networks that change over time, which could not be done by just inferring a Markov network using as if these observations are ID. Another case, another sort of things that we could do with this is here on the right-hand side we are putting known interactions between genes. So somebody has performed an experiment and they found out that two genes do interact. And then what we're doing is the blue points are the output of an algorithm where the edge is put in time when these two genes interact. Okay, and then we can go and validate, for example, with MSN and doc. Our algorithm infers that there's an edge during the embryo phase, which can sort of be justified by the fact that these two genes are related to the shape of an embryo. And for example, for SNO and these two genes interact to drive development of multiple eyes in a fruit fly. Okay. So this is again how one could use to explore a complex system and gain some insights about interactions that otherwise we wouldn't be able to obtain. Okay, and then maybe just to conclude with some theoretical results we can obtain here, we sort of can prove things that we would like to one would hope to be able to obtain. So under some suitable assumptions, one can show that. So I'm talking about the smoothly changing networks. So if we assume enough things, then we can estimate the graph at a certain time point consistently with a high probability. And so the conditions are standard in the literature on high-dimensional estimation. In particular, we require that the model is identifiable, meaning that the population version of Fisher information matrix is satisfies certain incoherence conditions. We require that the correlations between two components are smooth functions over time. So in particular, we assume that the second derivative is uniformly bounded by a constant. Kernel satisfies some regularity conditions. And then if the parameters are chosen in a sort of an optimal way, the graph is going to be recovered correctly. These two assumptions require telling us that the node degree cannot be too large, while this tells us that partial correlations or the elements of the precision matrix that are too close to zero will be likely missed out by an estimation procedure. Okay, so with this I'll conclude, and are there any other questions?
Thanks, Mladen.